Hello everyone and welcome to our fourth lecture in our course F1TENTH Autonomous Racing. In this lecture we will show you a little bit more of the foundations for autonomous driving. In this lecture we will talk about the PID controller and the Laplace domain. You probably remember both of these topics from your control courses, but we think that we have to bring back the knowledge about the PID controller and the Laplace domain to show you what is necessary to set up for the autonomous driving algorithms later. This means we will need the PID controller in different parts of our vehicle, and the Laplace domain will give us the possibility to analyze our controller or our control system later. So what we will do in this lecture is, first of all, that we show you in an introduction the tracking of a reference signal. What does it mean to have a reference signal, and what does it mean to track such a signal? In the second part, we will make a deep dive in the PID control. We will show you on the example of a path tracker how to apply a PID controller. Part number 3 will be the analysis of a control system with the Laplace transform. Here it gets a little bit more mathematical, but no worries about that. And number 4, we will show you a first application where you combine all the knowledge from part 2, the PID control, and part 3, the Laplace transform. My name is Johannes Betz, and today I will show you all of these topics. Let's start with number 1, tracking a reference signal. So first of all, what I will show you today is what is control engineering. I think all of you heard that in your engineering courses before. And in control engineering, we are focusing on modeling a diverse range of dynamic systems. We can think about mechanical systems, we can think about electrical systems, and for all of these dynamic systems that have moving parts, that have electrical currents that flow, for example, we will design controllers that will cause the system to behave as a desired manner. Which means we want to do the system something, like our car to stick to one path, and we need to design a controller that is applying specific parameters to our system. Here's for you to remember what are the different types of modeling you can achieve. It's like you have a simple input and output with a process, like for a simple algorithm. In B, you see here that you have a feed-forward controller, which means that you have a desired output response that you want your system to achieve something. You apply a controller, and you have an actuator that achieves something later, and you have an output that is desired, that is your desired output as before. And in the last part, this is the most important part for us today. Therefore, I will highlight this. This part is what we want to achieve. We have a desired output response, we have a controller, we have an actuator and a process, and we have an actual output afterwards. But this output is better than this output here because we are having a feedback loop. And in this feedback loop, we are integrating a sensor, we are integrating a measurement input that is creating an error afterwards here. And this is what we do in control engineering. We design such feedback loops in the controller to achieve the desired output afterwards. So, for example, imagine we have our F1TENTH car here. what you can see here, the highlight is the motor controller of the car. And what we do, we want to track a reference signal to achieve a specific engine speed. So what we do, we hand in our reference signal, in this case it's 60 RPM, to our controller. The controller is generating a signal. In this case, it's a pulse width modulated signal. This pulse width modulated signal has always a specific duty cycle, a full cycle, what you can see here. This full cycle has one part which is a digital 1, what you can see here, and has one part which has a digital 0, what you can see here. And by shifting the length of both parts, we can achieve a PV, a so-called PWM signal, pulse width modulated signal. This pulse width modulated signal then is going directly into our motor, our electrical motor. And this motor is achieving an electrical current with this pulse width modulated signal and is outputting a motor speed or an angular velocity. But this is our physical system here. If we are in the field of control systems and control engineering, we will describe it a little bit more different with our control system here. Again, we have our reference signal, which we call RT, with 60 RPM here. This signal is going inside our controller. The controller is generating a control output, which we call U from T here. In this case, it's the electrical current. And this information is going into our model or our plant, which is the motor, and is creating an output X from T here. We will see here now the signal where you have the control input, which is our electric current in blue, which is like a zigzag here. And we have followed afterwards in green here the response from our motor, who is trying to achieve a desired speed. It's going a little bit up, and then here is achieving the speed afterwards. This is what we mean when we say we want to track a reference signal. Here it's 60 RPM. How we can do that? We have to get to a higher control input, a higher electrical current, and afterwards we receive the signal. And the same you can imagine when we're thinking about autonomous driving. In autonomous driving, we want our car to stick to a specific path, a specific way we define in advance, and we want our car to stick to this path. And what we are designing here is a control system. In this case, the control system has a reference signal R from T, which is like 1 meter. We're designing a controller, and this controller is calculating again the control input, which is here the steering rate of our car. This is the same what we people, we humans are doing with the car. We're applying a control input and we're decreasing our distance d, for example, to the wall, which is afterwards the output for our system. But this is like an open loop system. We want to be a little bit better because we want to enhance our control system with a so-called feedback error. This feedback error, what you can see here, is generated by setting up a loop where we feedback our output signal here back to the reference signal, and we calculate it with, we have our reference signal R from T and minus our feedback signal X from T. And this is how we can achieve an error. And therefore, we are not only inputting our reference signal anymore, we are inputting the difference between our desired reference signal and the actual output signal, which means we are getting here much closer and much faster to our desired system output. And this is what you need to know when we're talking about tracking a reference signal. You have to remember how to set up your control system, which means you have to define for yourself what is the reference signal, what is the control output signal, what is the control input signal. You have to define for yourself where is the feedback loop, so which information do you need to feed back into your system. We will learn later with the car that we have to measure the information, additional information, to create a much better error, tracking error, or let's say control error for our system. This is what you have to remember from part number 1. Now let's step back, or let's step forward to part number 2, the so-called PID control. I'm pretty sure that every one of you has heard of this name before. And now we will tell you what this is all about. We will start with part number 1, the so-called PID controller, or better said, proportional control. Imagine you have a car here, and this car is driving with velocity here. This is a constant velocity, and you, as a normal car, you can choose the steering angle, which means you can steer the car to the left or steer the car to the right. And the goal is that this car is following this line here. And now there's a question for you. How can you achieve to follow this line here? Do you set a random steering angle? Do you set like a constant steering angle for our car? So what do you think is the best way to achieve driving at this line here? Okay, obviously a random steering might not be helpful here, and in addition a constant steering would lead to a shoot over here. So what we can do in this special case, we set up a special variable for us. And this variable we call the cross-track error. And this cross-track error is measuring the distance from the center mass of gravity of our car to our reference line, or the line we want to drive at. And what we say now, the steering of the car must be in a proportion to the cross-track error, which means we have a so-called proportional, or the abbreviation PID controller. And this is the complete magic we have here. So the idea is the applied control input is proportional to the cross-track error. So we have it here again. Our error is the reference signal minus the output signal. The larger the current error E from T is, the larger is the applied input to correct it. Which means if we have like a high cross-track error, we have a high steering angle. If we have a small cross-track error, we have just a small steering angle. And the control input we generate, U from T, is that we multiply our cross-track error with a gain variable Kp. And this is the magic behind the proportional control. But we will now go a little bit more into detail there. I enhanced our setup. I give you here the coordinate frame, X and Y, and we are driving here again with our car. And what we are saying now, first of all, we want to drive on the reference line here, and we want to drive parallel to the wall. So again, we have our control input, which is the steering angle, and this is the output. The control input is our steering angle, and this is where we achieve the final movement of the car. Again, the velocity will be constant here, and the goal is keep the car driving along the center line, which means from a mathematical point of view, y must be 0. And then we say we drive parallel to the walls, which means our steering angle theta has to be 0. But this here is wrong. We need like a better way of displaying that we are driving parallel to the wall, which means theta cannot be achieved to be 0. What we do better is that we say we multiply L by the sinus of theta and want this here to be 0, which means the distance we calculate here from the car needs to be 0. Which means the better way is after driving L meters, we want to be still on the center line. So we will minimize the horizontal distance after driving L meters, and this gives our car a little bit more time to achieve the center line and not focusing on theta 0 only here. So again, our goal is to keep the car driving along the center line. Y is the distance from the center line, and L multiplied by sin of theta is the difference between the destination of the drive straight and of driving at the correct angle theta. And this term, of course, is getting 0 when the car is driving on the center line and the car is aligned to the walls. And our error term is then, as a conclusion, the combination of both, which means we add y to L multiplied by sin of theta, and this is our error term here. So now we achieved to set up a mathematical function that defines our error term. And we want to minimize this error term. This is our overall goal. So now we have defined the error term on a mathematical expression, and we can check now if this is valid for us. So first of all, we can check if y is bigger than 0, which means our car is on the left side, which means we want to steer to the right, which means afterwards theta needs to be less than 0. And again, L multiplied by sin of theta, which means the car is now on the left in L meters, which means we want also steer to the right, theta is less than 0. And complementary, here if y is bigger than 0, the car is on the right, and L multiplied by theta, the car is on the right in L meters. And also, both thetas are bigger than 0, which means our calculation is correct here. So, what is the overall conclusion for us, our mathematical expression? We have to set the desired angle. Remember here, we have our arrow here, and we set up our proportional control, which means the desired angle, theta d, is our, sorry for that, is our Kp gain multiplied by the arrow, which means minus y minus L multiplied sinus theta. And this here is now our mathematical expression with all the available physical parameters we have. We can easily calculate to create our proportional control. Now here is a small video for you where you can see where we set up such a proportional control. What we see here, we will overshoot with this algorithm very easy. The car will oscillate around this center line, or the center line we try to follow really easy in that way, which means we need to tune this parameter first of all so it works out better. So what is good about the PID controller? The controllers or the P controller improves the steady state accuracy by decreasing the steady state error. Remember, the steady state error is defined as the difference between the input and the output of a system in the limit as time goes to infinity. In addition, the P controller, as the steady state accuracy improves, the stability of our system also improves. And what we always want to achieve in the control system, that it is stable. In addition, the controller also helps in reducing the unwanted offsets produced by the system. What's bad in a P controller is, due to the presence of a P controller, we got some offsets in our systems, and the proportional controller also increases the maximum of the overshooting of the system, what you can see here, which is achieved by a P controller. So what we have to do now is thinking a little bit more advanced. So how can we advance our calculation so it's receiving better results? So what we need, when the car is turned enough to reduce our defined error, it won't just not overshoot the center line only. So we need to modify it. And we need our car to react a little bit more quickly, because the P controller is also really slow because the car needs time. And we can achieve that we integrating a second part, the so-called derivative part, the D part, and therefore we create a PD controller. You can imagine it like this. We will now approach the center line more slowly, but steady as we reducing the error. So when a car is turned enough to reduce our defined error, we integrate the new term, so our car figures out that it can steer like to the other side again, because it's approaching the error itself. The car will counter steer or like steer up, and we're approaching this curve more smoothly. So the idea is now we apply an early corrective action that will predict which way the error is going, and therefore if it is decreasing or increasing. Decreasing or increasing, this is our word for a derivative, which means a simple prediction is to apply with a derivative gain, and this is also based on the error. So now we have our new derivative gain, KD, and we have our derivative part, which means d et du dt. So we add this new term to our steering angle calculation for our PD controller setup, which means we now advance our P controller to the D controller and have now integrated an additional parameter. So this is better than our normal P controller, but in addition, we have disadvantages here. If you have a systematic bias, like a broken steering that creates a steering drift, it will cause a new and a big cross-track error, and we will not achieve defining the center line. In addition, the trajectory correction takes longer because it needs time to smooth out, which means like in a proportional controller, we might just head our steering, drive straight to the center line, but overshoot afterwards. Now it takes a little bit longer, and we are approaching the curve more slowly. So you can see here now a video where we integrated KP and KT controller, and we overshoot here a little bit too, but we are approaching our curve after our reference line afterwards. So PD controller is now finished. Now we're coming to the last part, because we are not really satisfied with this setup. So we want to enhance it a little bit more. So again, we are driving here with our car, and imagine if you drive a car and your normal steering mode leads you to a trajectory away from the goal. So then you normally realize for a specific period of time that you can't get closer, and you will steer more and adjust to the bias. And what do you need? What do you need for that? So you need a sustained situation of a large error, and that means we measuring the sum of the cross-tracked error over the time. So the idea is the steady state error accumulates over the time, and we apply an additional correcting input that is sensitive to the total error so far. So you see here now the additional trajectory our car is approaching. It's much faster. It's going much faster to the reference line and sticking more closely to the reference line. So we add now the sum, or let's say the integral of all cross-check errors, ET, have an additional parameter KI, which defines our gain, and creating the integral over ET. And we add this term again. We created this one and add it now to our mathematical calculation. And with that, we have all the parameters together to calculate a correct steering angle theta. And with this setup, we are good to go to drive more advanced. So to sum it up, this is our PID controller based on the arrow E from T, and this arrow term is defined again by the distance to the reference line and the path along the wall. Just in this case, so your arrow term might be different, but this equation over here, where you calculate the steering angle, you can apply that to all of the control problems you know. And again, this is defined by the proportional term, by the differential term, and by the integral term. A PID controller, another term is three-term controller, is now a control loop mechanism to employ feedback that is widely used in industrial control systems and a variety of other applications. And again, the PID controller continuously calculates an error value, E from T, as the difference between our desired reference or set point and a measured process information. And he applies a correction based on the proportional first part, differential second part, and integral part. Hence the name PID. And here again, I brought you a simulation where you see again that in red here is our reference line. We want to achieve that. And if we apply different controllers, we achieve different outcome of our system afterwards. And to see it on the car, because you want to apply it on the car here, the car starts off the center with the direction to the left. The car starts and corrects very fast with like one overcorrection, and the overcorrection decreased in comparison to our first video. I will play that for you again, just to give you an impression of what you just saw in the simulation, and now you can see it here on the real car. So now we learned how we can set up a PID controller, but what's the magic behind PID? It's basically the tuning, which means we have to find good control gains. You remember, each of the different parts, PID, had an additional control gain, which means these are the parameters we can tune, and these parameters can vary from system to system. So the tuning of PID controller needs experience and hands-on tuning with experiments, with simulations. In addition, it depends on the system you have. Like a PID controller for our electrical engine, which I showed you in the beginning, might be different from the PID controller of our reference tracking. In addition, what can the system tolerate and what's dangerous and what's okay for our system so it doesn't create or doesn't lead to a crash. And in addition, it depends on the desired performance characteristics we have. And what we can use are two things we can recommend you here. First of all, heuristics. There are heuristics we can use, for example, the Ziegler-Nichols method. We put additional material there. You can read about that. Or you might just set up an optimization algorithm. For the PID controller of your F1TENTH car, it's probably enough to use the heuristics like the Ziegler-Nichols method. But for bigger systems, we might use an optimization algorithm. So to sum it up, you just learned what a PID controller consists of, and that the main parts is the error and the control gain parameters, and the combination of both of them in a derivative, integral, and proportional part leads to a PID controller. So, and now we're coming to our third part, the Laplace transform. So I said to you at the end that we have to tune our system, that we have to do experiments, and that we have to get like an insight of our system. Of course, we can just apply it to our car and drive with the car and see afterwards what it's doing. But this is like taking us a lot of time, and we need the hardware, but we can do it like with mass only and in simulations a priori. And to do that, we are using something called the Laplace transform. Perhaps you remember this also from control engineering or from your math courses, but we will wrap it up here. So in mathematics, the Laplace transform is named after its inventor, Pierre-Simon Marquis de Laplace. And what he's doing, or what he invented, is an integral transform that converts one function of a real variable t, or often called like time, t is time, to a function of a complex variable or a complex frequency. So this is just the basics, like we transform one from the time space to the complex space, or what we call the frequency domain. Time domain, frequency domain. And this is what we achieve with this math. And first of all, why we want to do that. So many dynamical systems are modeled or displayed by ordinary differential equations, so-called ODEs. To predict the system's behavior, we must solve these ODEs. And the Laplace transform provides a relatively easy way to solve ODEs by the formal rules of algebra, which means we're transferring something from derivative terms to simple polynomials, which we can calculate very easy. And in practice, however, one has to deal with systems that one does not know in principle and whose properties should be measured first. This is also a really big issue here. So to give you an example, this is the well-known mass spring damper system. And we can see here, we have a mass in our system, we have our damper coefficient, we have a spring coefficient, and the movement in x direction of our mass is applied by a force. We can set up an equation, a differential equation for that, which means we calculate, we multiply the mass by the second derivative of x, acceleration, add there the multiplication of the damper spring by the velocity, second derivative of x, as first derivative of x, and we multiply k with the x factor. And this equals the force. So we can set up these differential equations, but to solve this in our time domain is super difficult. So we want to solve this differential equation like an algebraic problem, again here, we're transferring it from the time domain to the frequency domain. And then we have a polynomial we can easily solve. So we have a look at the mass here. We are using the so-called Laplace integral. For the Laplace integral, you have always this variable here that looks like an L, which means we are applying the Laplace integral to our function f. And which means we multiply it by e to the power of st, bring the integral over the complete function, and create therefore our transfer function f from s. S is a complex number here. It should be clear that we use one-sided Laplace transform, which corresponds to all t's bigger than 0, so all non-negative time. The Laplace transformation takes the causality of the system into account. Since it only starts at the time t equals 0, it is capable of being used for most real signals ft, which are plotted over the time t and for the most common differential equations to calculate the reversible unique image function fs. So to repeat it here again, we have something that is existing in time domain t, and we transfer it with the Laplace integral to the frequency domain. And here is an overview again of that we have an input x, we have a plant and a function, and we have an output y. And with Laplace, we can go here over the system, which means x is transferred to x from t is transferred to x from s. Our plant h from t is transferred to h from s, and our output y from t is transferred to y from s. The math behind the Laplace transform or the transform properties we will not show you today because this is like basic math or basic control engineering math, and we will just fresh up your knowledge here. So the Laplace transform relies on main properties like the property of linearity, the first shifting theorem, the differential and integration, which means there are specific properties how you can transform your normal math or your normal differential equations to the Laplace domain. And now, for example, we will have a look at the linearity part, just to give you an example here. So we are now having a function f from t and g from t. Both of them are in the time domain. We have a and b that are constants in our systems, and we want now make a Laplace transformation of the complete function. And what we say that we can put out or like pull out both of the constants here and say it's the same if we just pull them out and make the Laplace transformation on the functions itself. So now you can just believe me with that, or what you can also do, you can prove it. We wrote down the proof for you where we did the Laplace transformation for you here. You can have a look at this more in detail, but more or less we are proving in this case again that this is the same. So, which means there are specific properties. So before you start with transferring something into the frequency domain with the Laplace transformation, please make sure that you know about the properties. In addition, for us engineers, there is always a table that is available which contains information about the Laplace transform, which means if we have a specific value in the time domain, for example, 1 here, our constant 1, in the time domain, this is displayed as 1 divided by our complex number as in the Laplace domain. And for all mathematic expressions, we have here different transfers, and you can have a look at this table to make your life a little bit easier. And just for the completeness, we brought here one example to you. I will not go here into detail, but we showed you here that we have one differential equation and we set up the Laplace calculation for you here, which you can solve. But an additional link gives you more information about the Laplace transformation here. We will not go here into detail because this is just a refresher for you to show you what is possible, because we want to use this information to set up our Laplace domain or our frequency domain for our control system. So what we do is we have now our control system here. Remember, we have the reference input. Here we have our error. We have our output signal, we have the control input signal, and we have the controller and the plan. So first of all, we setting up a closed loop system. So we have the controller and the plant in one. So it's a little bit more compact. And what we do now, we are creating a transfer function. The key advantage of the transfer function is, again, their compactness, which makes them suitable for frequency domain analysis and stability studies afterwards. So the transfer function itself, it suffers from neglecting initial conditions. Not only does the state-based representation serve as an alternative to these transfer functions, but also it is not limited to linear and time invariant systems, and it has the following advantages. And then again, by transferring the control system from time domain to the frequency domain, we can easily see if the system is stable or not. Remember here, I will say it at the end again. Stable in this case means that our control output is controlled. So it's not like getting bigger and bigger and bigger and leading to an uncontrolled system again. So we are creating here the transfer functions, and our control loop consists here of our several interconnected blocks again. And by transferring it to the frequency domain, we can describe the whole system with one transfer function only. We have here displayed you in red. And for the interconnection of the rules, for the interconnection of the individual blocks, we will use the rules what we saw before. Like we have one number, one variable in our time domain. We use the transfer table, we transfer it, we make the calculation, we make the math, and create our transfer function afterwards. So, for example, this is the model of our server. Here you can see the complete model of the system, which is modeled in the time domain, and it includes both plant and controller. Because we have the controller part with our proportional gain here, we have the error, and we have the modeling, the plant modeling of our motor. And we can set up here again our differential equations, but as I said before, we want to now transfer this one from time domain to the frequency domain. And here we see now the example of the motor system transferred to the frequency domain that includes both motor model and the controller. And what we can see here, what we always have the expression is the output divided by the reference, and where we display here our transfer function. And then what you can do afterwards, we integrate the real variables for it, like here the rotating engine, motor speed. So we can rewrite our, let's say, variables only with real physical parameters to express a calculation afterwards and to have a look at simulations. So what you can see here is that we see the step response of our system. So what we have done, we applied an input to our calculations, and we see a step response of our engine afterwards. And what we can see, if we apply different parameters, we get a different output of our system afterwards. So the acquisition of the properties that can be done by recording step and impulse responses, what we can see here is the step response, or by measuring the frequency response. Step response, impulse response, frequency response, and the original differential equations have similar information for us because they all contain this description of the system in different form. And remember that again, why we are doing that. In our differential equations, it's difficult for us to solve the system. Here in the Laplace domain, we have this simple calculation on the left side where we can apply the real parameters and we get an output afterwards. And this we can plot and then analyze. And the same, what we can do for our models itself is then for our controllers. Like displayed here, the PID controller, it reduces the rise time, it increases the overshoot, and it reduces the steady state error. The proportional controller in the Laplace domain is no more or less the error multiplied with a factor Kp, what you can see here. The closed loop transfer function of the above system with the proportional controller is then Ts, what you can see down below. And you can do the same with your integral controller. And we can see here again, if you're applying one specific input, like here we are applying a step input to our system, which is defined in the Laplace space, again, what we saw before as one specific parameter in time domain, and in the frequency domain, 1 divided by s. And we create an arrow for that again and can create a transfer function afterwards. So again, why we are doing this? Because we want to tune our controller. We want to figure out the individual parameters for our control gain, Kp, Ki, and Kd. And we can analyze our system regarding the stability. Again, the system is said to be stable if its output is under control. Otherwise, it's said to be unstable. A stable system produces a bounded output for a given bounded input. So again, it's not just like that our output is getting bigger and bigger and bigger. In addition, we want our system to following the reference quite fast and easy and smoothly. And we want to have a transient response here. And with the creation of our Laplace transformation from the time domain to the frequency domain, we create the possibility that we can analyze and tune our system afterwards. So this was a lot of input. This was a lot of math input for you. And I think a few of you have now to remember all this stuff again from your control engineering lectures. So we will now wrap up everything we learned in the past 50 minutes and apply it to one specific function. And we do it with a little help, so you can do it more easily and faster. We are tuning now our motor controller. Our motor controller is consisting of a P and I and D part, which means we have a PID controller here. And we will use a tool for that, the so-called VASC tool. You can download it here. And this VASC tool gives us the possibility to connect our computer with the motor controller of the electrical engine of our F1TENTH car. And after you did a firmware update, you can select our motor configuration we created from you. It's in an XML file. And what you can do, you can just drop it in here in the VSC system, and you write it to the motor configuration. And what you can see here is the down arrow and the M. And with this one here, you will download your current configuration to the engine. If you create new variables, you create a new motor configuration, and you have to download it again. So note in the future, you'll have to press this button whenever you make a change in the motor configuration. Without that, it's not getting applied. So, but this is just a setup, and you will find more additional information in the tutorials. So what we do, we start tuning the speed PID controller. This PID controller controls the speed of our engine, which means I give the information that I want to have 1000 RPM. The controller of our motor controller achieve this for us, and we can tune that. So to see the RPM response from the motor, navigate to the real-time data tab under data analysis on the left, what you can see here. You have different information about the system, like the current the motor is draining, the temperature of the motor, or the RPM, or the rotor position. So all useful information. And to click the stream real-time data, you can click the button here on the right. And then you can actually put the car on the table, activate your motor with your wireless controller, and see the real-time data of the engine. So again, we have now our system. We have now a controller, and we say we are not happy with that. So what we do, we gain measurement insights to our system with the real-time data stream here. And now it's time to tune it. And again, what are we doing? We are applying specific signals, for example, the so-called step response. That gives us information about the system's behavior. So to create a step response for the motor here, you can set a target RPM. We create that here. A target RPM, you can choose between 2000 and 10,000 RPM. Then you click to the button next to the box to start the motor, which you can see here. And be careful about that, because the motor will spin afterwards. So you make sure that the wheels of your vehicle are clear from objects and is not located on the ground. The enter, click the enter or the stop button right next to it this is for stopping the system, and this for applying step response. And you can see here now the measurement of the step response. So here's the measurement. Our motor is not doing anything. We have the step response, which is really high, and then goes up to 5,000. And we can see the behavior of the engine afterwards. You want to look for a clean step response that has a quick rise time and 0 to very little steady state error. And then you can inspect the system, and you can adjust accordingly by navigating to the PID controllers under the motor here, PID controllers. You see here your KP, your KI, and your KD parameters. You can change them and apply to the motor again. And with the rules of tuning, I told you before, like either it's an optimization or you just use the heuristic, you can gain them and apply them. And if you're seeing a lot of oscillations Try changing the speed of the KID filter, which is coming in addition here. But now you can play a little bit with the system and gain the insights. So we are at the end of this lecture. I hope you enjoyed getting a refresher in the field of PID controllers and the Laplace domain. Remember, here we are applying a lot of stuff from the math, so we can choose a lot of systems that are provided for us, like the simulations or calculations from simulation environments like MATLAB, or we can use Python code to calculate a really good insight. But we need to measure our system, and we need to insight and inspect the system behavior afterwards. Thank you very much for listening today. If you have questions, feel free to reach out to me. We see each other the next time.